Hi everyone. So now we are going to see the inner product spaces. So inner product space, in case we are going to see that specifically in linear algebra. Okay. So the inner product space, we have to see the definitions. Definitions means it should follow some of its axioms. Okay. So let in that vector space, let V be a vector space. So V generally we used to have that as a vector space over F, over F means F relates to field, okay, that contains some scalars. So here an inner product can be defined using every ordered pair. So you have to arrange that in x, y, z, that may be more than that. So we are having according to that. So this following axiom should be followed with vectors and its scalars. Okay, vectors belongs to x, y, z and scalars it may be c, a, b like that. Okay, now we have to assign according to that. So here we have x, y, z are are vectors and c be a scalar. Okay, so with that the following axiom should be solved, that is x plus z. So we can say that inner product. So inner product x plus z comma y equal to inner product x comma y plus inner product z comma y. Then B inner product c x comma y, c is some scalar, right. So we have to notify that. So equal to some c into, we have to take that c commonly outside and we are that will be inner product x comma y. So we have to say this as inner product, or we can say that x comma y, that is enough. Okay. Then inner product x comma y the whole bar equal to some y comma x. So if we have to in this one we have to interchange that one and we have to write. So where this bar denotes the conjugate. Okay, conjugate, then x comma y, fourth condition is x comma x greater than 0 if x is not equal to 0. Okay. So this is specifically known as inner product. Okay, inner product space we will define in denoted by using this thing. Then we can that can be expressed as in a set of ordered pairs. Okay. So this is the definition. So first condition satisfy these four conditions, that's major one. So if this does not satisfy this condition, then it won't be a inner product space. Okay. Now we are moving on to the theorem. So the theorem also represents that one. So we have to solve that by using this inner product space. Okay. So let V be an inner product space. V already be a vector space. Now we are having V is a inner product space, that is it should satisfy these four conditions. Okay. We can apply this in this theorem. Okay. Then for x comma y comma z belongs to V and C belongs to C is scalar. These are all vectors. Then this following axioms are true. We have to prove that one. Okay. So now we have the theorem x inner product x comma y plus z equal to inner product x comma y plus inner product x comma z. Okay. Then B x inner product x comma c y equal to c bar inner product x comma y. Then inner product x comma 0 equal to 0 comma x equal to 0, and then inner product x comma x equal to 0 if and only if x equal to 0. Okay. Then fourth condition, if x comma y equal to x comma z, that is inner product x comma y equal to inner product x comma z, then y equal to z. So next the theorem we have to solve the proof. Okay. That already we have V is vector space, right, and then x comma y comma z belongs to V, these are the given condition, and C is scalar. So this is some scalar, these are all vectors. Okay, vectors, that is denoted by using this one. Now we have to solve each one of the thing. Okay, we already V vector space, rather than that it is an inner product space, right. Inner product space, it should have satisfy the following four properties, right, that is four axioms. So, with that we will be solving this one. So, first one A, first part to prove which one, x comma y plus z equal to inner product x comma y plus inner product x comma z. Okay. So, that is we are considering this one to prove x comma y plus z equal to. So, we already know that in an inner product we already know x comma y equal to y comma x the whole bar, right. So, instead of that we can use that one. Okay. So, that 4 axioms is solved, sorry, it is proved, it is, if it is that one only it will be an inner product space. Now, it is inner product space, right. So, we can use these 4 conditions everywhere in this theorem. Okay. So, now we are moving on to that one. So, it should interchange that one. So, we have to interchange x to y and y to x with that whole bar, right, whole bar. Okay. So, now we are splitting that one, we are splitting this one. So, if we split and write, what will we get? Plus okay, we are splitting and we are writing it is y comma x. So, you have to split this one. So, already that is also in axiom, this is axiom B, I think, this is axiom A or axiom x plus y z equal to x plus z, sorry, x comma z plus y comma z. We have to use that axiom too. So, that axiom, this one y comma x the whole bar plus z comma x the whole bar. Okay. So, now again we have to rearrange and we have to write that one. So, if we write, we will get the proof. So, y comma x can be written as y comma x the whole bar can be written as x comma y plus z comma x the whole bar can be written as x comma z. That's all. So, this is the proof which we get. Okay. Next one B. So, to prove x inner product x comma c y equal to c bar x comma y. So, again we will be using this condition, that condition is c y comma x. We have to interchange that one and we have to put bar on this one. Okay. So, now it is actually simply c bar y bar x. No, wait a minute, sorry. So, we have to write c bar, we have to take c bar out and we have to write that one as y bar comma x, hold this one. So, now c bar is x comma y. Again we have to apply this theorem, apply this property and we will get this one. Okay. So, now we are moving on to third one C, that is inner product x comma 0 equal to 0 comma x equal to 0. So, we have to apply again that property. So, again we have to apply that property and we will be getting to prove this one. To prove this one, we take any one of this one, x comma 0 equal to. So, this can be written as x comma 0 into x, 0 can be written as 0 comma x, right. Then we will take out 0 commonly outside, x comma x. So, 0 into anything equal to 0. So, therefore, this becomes 0. Okay, that is all. This is the proof of this one. And D. So, we have to prove this one. So, if x comma x equal to 0, if and only if x equal to 0. So, we have to take one thing and we will solve, that is enough. Given if x equal to 0, if x equal to 0 in this one, what will we get is we have x comma x, right. So, we have to solve that becomes 0, right. So, now instead of x we will be applying 0 comma 0, what the answer is 0. Okay. So, next one, last one we will have if x comma y, x comma z. So, we have to write in inner product, this is given. Then what we have to prove is to prove y equal to z. Okay. Then we have to consider this 2, x comma y equal to x comma z. Okay. Now we are bringing this one this side, we will get that becomes minus, right, x comma z equal to 0. Now this is inner product, right. So commonly we can take out as x minus x comma y minus z equal to 0. So that is 0 comma y minus z equal to 0. So this implies y minus z equal to 0. So therefore y equal to z, that's all. This is the proof of this one. Okay. So from this one we can, if it is an inner product, we can solve these conditions easily. Okay.